Now, our next speaker, I'm very pleased to welcome Professor Heier. And Professor Heier, of course, is one of the leading scientists in wind energy. You used to work at Kassel University. I think officially you are retired, but still working with the university as well. University where Fraunhofer Institute is based. You're also closely related to them. Author of many standard books, and I just took one from the shelf here. That's a German version, but I think there's the English one as well. And Professor Heier, you are the expert on more the electrical side of that. That's what I'm not so, of course, good in. And I'm now very pleased to invite you and hand over to you to give us an introduction, overview of the technical requirements. Professor Heier.
Yeah, thank you, Stefan. It is a pleasure for me to support your effort work in the wind energy, World Wind Energy Association. Now I will welcome you all worldwide to this technical part of my presentation. I will give you a small overview over the general aspects to integrate wind turbines, wind farms, and so in the electrical grid. So, it's not working. Stefan?
John, can you help?
Yeah, you should be able to move the slides with your mouse or keyboard.
Yes, I tried. Yeah, no. No, it's too far. Yeah. Okay. So I think it comes a little bit later every time. So I will give you a. No, it's not possible. I give you a short introduction, and then we come to the grid integration, and then to further aspects. So at first, I will show you the 20 years development of the wind energy here. Every time other things are. So, and now you see I start here with 1982 with this very small wind turbines with about 20 kilowatt, and 2000 we come to the 2 megawatt, and 2002 to the 4.5 megawatt wind turbines. It was a very strong development, and you can say about every 2 years we doubled the power output of the wind turbines, and until the 1 megawatt turbine 1994 about we have had a dominating Danish concepts with stall regulated wind turbines and direct grid coupled asynchronous generators. But over 2 megawatt, it is not more possible to work with this very easy systems. It means we need here high sophisticated systems. It means with pitch regulation and speed variable operation. It means with inverter systems. So, and after 2002, we expected that in a short time we will come to 5 to about 10 megawatt. But these wind turbines have been a little bit extended to 6 or 7.5 megawatt, but not more. But the next step was going back to, let us say, like this market leader, to the 5 megawatt class, but wind turbines with a much higher diameter. And now we come more and more to the 4.5 megawatt turbines until about 170 meter. And the background is that we have a capacity factor of about the double. It means we come from about 0.15 to 20 to about 30, 40%. So, and this means that we can use the grid much stronger. Oh. But now you see we can expect in the next time very large wind turbines in the size of 12 and 15 megawatt power output and about 220 meter diameter. This will come in the next years. Oh, and here you have the picture of the installed wind power capacity, and you see here about India has installed power of about 40, Germany about 65 gigawatt, or you see here 700 megawatt, here is 100,000 megawatt. It means 100 gigawatt. Yeah, Germany about 65, and USA has about 150. China 255. What we expect, and Europe about 240 gigawatt. And worldwide, we will achieve in the end of the year about 700 gigawatt. In relation to other installed power, you can say in Europe, in USA, and in China, we have about 1,000 gigawatt installed electrical power. Yeah, this as the size. China has coming up more and more. Yeah. So, and now let us come to the grid integration. And you see in this picture that nearly all the wind turbines are designed in the low voltage level. It means that the equipment for these wind turbines costs about the half in relation to medium voltage design systems. And this is the background that all the wind turbines are designed in the low voltage level. Then we need on our grid connecting point a transformer to come up to the medium voltage level. In the most time it is 20 kilovolt. For special wind farm grids we have 30-35 kilovolt level, and then we come here to our grid. It means to the point of the common coupling. It means the point where the next consumers are switched to the grid. Yeah. So, and here you can see the voltage levels. In the low voltage level, we can integrate only very small wind turbines. Yeah. In the medium voltage level, about 20 kilovolt, 30 kilovolt, we can integrate single turbines, plants, and so some plants when you have about 1,000 megavolt ampere short circuit power, you can integrate about 100 megawatt in this level. Yeah, it means 10% about. But this is a very high relation. And in the 110 kilovolt high voltage level, we can integrate wind parks in the range of about 40-50 to about 300 megavolt ampere, yeah, megawatt. So, and for very high installed systems, it means 500,000 megawatt systems, we need the 380 volt level, the extra high voltage level, to integrate very large systems. Normally here are integrated also nuclear power systems and very large coal power stations. Yeah. So. I'm missing a picture. I'm missing the picture for onshore integration. Okay, I think it must be in your computer or so. Okay, here you see the offshore grid integration, Baltic 2. It means when we integrate offshore wind farm, then we have to bring the power together in this grid station, and until about 100 kilometer we connect this station by AC 110, 220 or 380 kilovolt, and when we go over this distance in the 300 kilometer, in the distance over 100 kilometer, 200 kilometer, then we need a high voltage DC system. Most designed for the 300 kilovolt level. Yeah. So, and now let us come to the grid effects. At first, I will come to the change in the short circuit power. And here I will show you this. When we have the grid like here, then we limit the current by this impedance. And it means we get a short circuit current. But when we integrate to this grid a wind park, then we get a short circuit current from the grid and a short circuit current from the wind park. And here in this picture you can see the short circuit increasing factor can be by a synchronous generator about 8 times higher, and this two dotted current means the subtransient value, and here the normal value. Yeah. So, and by asynchronous generators about 6 times more. So, but these systems are not more working in the modern wind turbines. We have only double feed induction generators or inverter feeded systems with asynchronous or synchronous generators. It means here we have a short circuit power of about only the nominal range of the current or the nominal range of the power, yeah, short circuit power. It means, let us say we have here a short circuit power of about 500 megawatt, and we integrate a wind park with 100 megawatt with inverter. Then we have here a short circuit current with 500 plus 100. When we integrate a double feed induction generator, it is 300 amps, 300 megawatt more short circuit power. Yeah, it means that we must design all this equipment special for this total short circuit power. Yeah, it's a very important thing. Next step will be the voltage variation. It means when we have our grid and we have a load, and now we integrate a wind turbine, and let us say the wind turbine will be fed by the load will be fed by the wind turbine, full or the half. Then we get an increasing voltage here. But this is not only the right thing. It is dependent also on the feeding in angle. It means that we can feed in a special angle. In a extra high voltage grid, we have a very large angle. It means we can calculate with nearly cosinus phi is 1, it means 98% or so, and then we have a neutral voltage feed in. Yeah, this can be a very good advantage. And you see in the international regulations we have a limit of 10%, and in Germany we allow only 2%. In other countries it can be more. Yeah. So, the harmonics have been a very large problem until the 1990s. But since 94, we come up with the IGBT inverters, Heier and Heier, and then we can integrate this inverter systems in wind turbines. And here you see this tolerance band control system, and when you have a small filter behind, then you have an exact, nearly exact sinus form, and so it is not more a large problem to integrate very large power in the grid, and the harmonics are not more so important. But I have in the moment also not a PhD, it is a master degree in this direction. Yeah. So other point are the grid resonances, and here you see in a wind park when we switch out all the wind turbines and we switch on the first, the second, and so on, here the 20th wind turbine, then you can see that the impedance is variating. It means that we have here a very high peak, or here we have a high peak, or here we have high peaks. This means when we have a feed-in current with this harmonics, it means the 37th harmonics. It means 37 multiplied with 50 Hertz. Then you get here a very high voltage in this harmonics, and this means that you have a voltage resonance. In the other side, you have here impedance near zero, and this means when you have a voltage and impedance nearly zero, then you get a very high current. It means we have here a current resonance point. Yeah. And so sometimes it can be critically special when you have large distance and a very strong calculated grid. Yeah. So in the 90s, I started the grid control by wind turbines, and here you see this measurement system, and we have shown in our interconnected grid here near Kassel that we can change in this time. It was a 500 kilowatt turbine. This was in 95 about. This was the largest wind turbine where we can change the reactive power here from 150 kilovolt per reactive overexcited to minus 25 megavolt ampere under-excited, and we go high to this level as before. Then we change the voltage from 402 in our low voltage grid to 398, and we come back again. Yeah, it means we can change 1% in our interconnected grid. This was a European project, and we have done the same in the Canary Island, Tenerife, and also in La Palma. And in these islands, in Tenerife, with about 600 megawatt installed power, we can change the voltage 3%, 5%. In La Palma, we can change the grid 10%. It was not a problem. Yeah, good. This was the result of Dr. Arnold, his PhD work also, and we have made a lot of investigation for grid control to hold the voltage about in the same level. The next step comes 10 years later. Then we have seen that we can change the voltage in the grid, and we can support the voltage in the grid. Then comes the grid code, but you see we have not one grid code. Every country has other grid codes, and in Germany we have also grid code from E.ON, from Vattenfall, and so on. Yeah, this is the next problem, that all the manufacturer have to fulfill all the conditions for every grid codes. Yeah. And here we have also made a lot of investigations in this case, special for double feed induction generators by Dr. Da Costa from Brazil and Mr. Gericke. He's now working by TNET. Yeah. Oh, and the prediction of the power is a very important thing. And in this PhD work of Mr. Gesino, he's now back in Argentina. He showed that in this picture, this was the full year 2009 simulated. And here you can see that we have here in this point, the green ones is a wind feed-in, and all the other is a rest power consumption. Yeah, you see here we covered the peak, but here we covered also the peak, and here you see we have very high peak decreased, but in this point you see we have here also the peak brought down, but also the basic level goes down, and this means it is in the future much more complicated to react and all the other power stations to these conditions. Yeah, and Mr. Gesino has created an algorithm so that he can predict very safety the power feed-in and so on, and then he has shown that we can drive down from about 35 megawatt to about 15 megawatt. It means we have here a negative power reserve, and we can come up from here 50 to about 40 megawatt. It means we have a positive power reserve, and so it is possible that we can work with the wind turbine as a power control reserve system. Yeah. So, let us come the last point, the wind energy benefits you see are that we have a fast control and reactive power control possible. The frequency and voltage support, it must be fulfilled in the grid code, and prearranged energy input via wind power by wind prognosis. And so we can also deliver the positive or negative reserve. Other thing is the spinning reserve of wind turbines. Then the spinning reserve of wind turbines is very high, and this to use, but we must come to other regulations. Yeah, and other point will be the fast power control. It means that in relations to nuclear or thermal power stations, they need minutes for very small decreasing factors. In a wind turbine, we can come in seconds to a power input 0. Yeah. Fast control of voltage dips. This we have also shown in the near of Braunschweig in a PhD work of Dr. Sayu. Dr. Sayu is now professor in the Applied University in Flensburg. And active filter to use for decreasing the harmonics and so on. Yeah. So other point will be connecting different climate zones and the combining different renewable energy sources. It means that we come to a high grid capacity when we can connect these parts. We come to more constant and frequency in this grid, and the energy balance between temperate climate, subtropical and tropical regions. So we can get a good balance. And the combining wind, solar, and hydro energy, the balancing effects in the meteorological and long term, and so on. Yeah, the hydro storage more effective to use, and so on, to grid frequency control and all what you could think so. It means that we can using expensive wind energy on the continents. Yeah? And for example, here I will show you the European and the African and Middle East region, and a good possibility or a good chance will be to build a ring grid between these countries. And though it will be a good possibility to stabilize the grid in North Africa and Middle East and Europe, and the problem will be that we must have very stable political conditions in these regions also. On the other side, we must see the disadvantage will be long distance electricity transmissions are connected with high costs, losses, and so on. The grid stability problems with increasing utilization and distance. It means that it is load dependent, and we get by high loads frequency deviations in different regions, and this means that we can have reactive power oscillations in this region. It means in the European grid we have this frequency oscillations between Romania and Bulgaria and Spain and Portugal here. The longest distance systems And here also in Libya, Egypt, Jordan, and Syria, before the war, we have spoken about this problem. They have had about 440 megavolt ampere reactive oscillating here in this grid. Yeah. Though you can see it can be a very good chance, but the political conditions must be better. Yeah. So, result and measures. The grid extension must be necessary or can be necessary. We can divide 3 zones at every country, continent. It means 3 in Europe, in Middle East and North Africa, and we can high voltage and or DC transmission lines between MENA and the European Union. The political guidelines for successful introduction of wind energy must be given, and the involvement of population for broad acceptance of the wind energy is very, very important. We see it now in Germany. Yeah. The first aspect at last are that we can wind energy converters and wind parks see as a part of virtual power plants and smart grids, and the direct supply of industry and consumers, the direct marketing of the wind energy, and blockchain in the energy sector. Thank you very much for your attention, and here in my book you will find much more. Here my English book and here my German book with about here 520 and here 570 pages. Yeah. Thank you very much.
Thank you so much, Professor Heier. This was, I think, an excellent introduction into, I mean, far beyond what I, as a trained political scientist, can of course cope with. But I know that we have many technical experts who I'm sure followed your presentation with great interest as well. And of course, we must be aware of all these technical requirements and conditions if indeed you mentioned that on one slide, which is our task as an association, if we want to convince and persuade political decision makers that a large share of wind power is possible and that it's also technically beneficial. So I suggest again, those who have questions, please write in the chat box. Professor Heier, you please also have a look at this chat window here if you can. Otherwise, we can also send them to you later.